Welcome. We'll now take a look at another example of finding a minimum sample size required in a study. And I've got a summary here of that formula for finding N for a desired margin of error and a confidence level. So the reminder here is that after we get our value for N, most likely it will not be a whole number, but we do need a whole number. And the formula gives us minimum sample size. So the value we get, we can't go smaller. So we always round it up to our next whole number. And I've gone ahead and put some common confidence levels here along with their corresponding critical values. So we did find different ways to find critical values, but it's just nice here to have the reference. And I did put a picture here of the process we used to find those values. So I'm just going to label this picture for this example where we'll be doing a 95% confidence interval. So that center area there would be 0.95. And then we had stepped through the process of finding alpha over 2, which in this case was 0.025. And so that z-score called z alpha over 2 is the z-score that puts alpha over 2 to the right. And that value, we learned how to find it several different ways, but that is 1.96. All right, so let's check out our example here with Anna. So Anna would like to estimate the mean weight of all the apples in her orchard. She will take a sample of apples and construct a 95% confidence interval for the mean weight. She is willing to use 12 grams as an estimate of her standard deviation. So in the formula, we're going to need something for sigma, and she's willing to use 12 grams for that. And she wants her margin of error for her estimate to be no more than 5 grams. So she wants to be accurate when she's done for the weight of her apples to be accurate to within plus or minus 5 grams. All right, so let's find the smallest sample size required to obtain her desired level of confidence and margin of error. All right, so Anna wants to estimate a population mean. I'm having us write that because later we'll learn to estimate a different parameter and we'll have a different formula for N. So this formula only applies when we're estimating a mean, as we are here. And she wanted to be 95% confident when she's done. All right, so let me write down our given values. So we have our z alpha over 2 of 1.96 for a 95% confidence level. And then she's willing to use 12 grams as her estimate for the population standard deviation. And her margin of error, E, is 5 grams. And we have everything we need. So our formula is N equals, in parentheses here, so we'll take our Z alpha over 2. That gets multiplied by sigma. We divide by the margin of error, and that whole quantity gets squared. All right, so I'm going to write this horizontally like I'll type it on a calculator. So 1.96 times our sigma 12, divide by my margin of, oops, not E, we'll put in 5, divide by margin of error, 5. And then that whole quantity gets squared. All right, so let's do this. So I'm going to type it in exactly like I wrote it, open parenthesis, 1.96 times 12 divided by 5, close parenthesis, and square. All right, I'm going to write down that entire value I see on my calculator, 22.127616. All right, so that is the smallest sample size required, but of course, Anna can't pick 22.127616 apples from a tree. That's just silly. So we have to have a whole number of apples. So since that's the minimum, you can't go down to 22. This is not normal rounding. So this is the lowest possible. So we've got to go up to the next whole number. So she's going to need at least 23 apples to reach her desired confidence and her margin of error. All right, so Anna needs to sample at least 23 apples. So collecting more data would be great. So we can always feel better about estimating our population if we collect more data from it. So this is just bare minimum. So at minimum 23 apples, if she wants to estimate the mean weight of all the apples in her orchard with 95% confidence and to be accurate to within 5 grams. All right. So the follow-up question here, it says Anna decides she would like to have a higher level of confidence that her interval will contain the actual true unknown population mean. So let's find the sample size she would need if she would rather be 99% confident that her estimate contains the mean while keeping the same margin of error. So rather than 95% confident, she wants to be more confident. So to be more confident, she's going to need more data, and we'll see that play out here. So for 99% confident, our critical value, Z alpha over 2. So coming up to this picture, if this middle area gets bigger, 0.99, 99%, the Z-score that makes that happen will be further from the center. And I'm going to scroll up here. That will be 2.58. So instead of 1.96, we're up to 2.58. She's going to keep her same margin of error. So she's not going to change that. Just her confidence is changing. And I'm sorry, that's 5. 5. It's her standard deviation. That is 12. Okay, I'm going to write the formula again. Always good to just practice writing formulas. It flows more easily as we continue to write. So Z alpha over 2 times sigma over margin of error squared. All right, so 2.58 times sigma divide by margin of error and square. All right, I'm going to enter that exactly again like I wrote it. And now, again, I'll write the whole number. You don't have to do that necessarily, but just so I have it in the notes, 38.340864. So I'm going to have to go up to 39 apples at minimum. So to be 95% confident in her results, only 23 apples, as opposed to more apples if she would like to be more confident. Okay, so the standard deviation that she didn't know, but was willing to use 12 grams as an estimate for it. So our next task is to look at problems where we don't know sigma. So we've been doing many problems where population standard deviation has been given, but if you're not collecting data from an entire population, it'd be pretty unusual to know that value. So we're still going to continue learning to estimate a mean, but we're going to switch to the case where the population standard deviation, sigma, is unknown. So we have to be really careful when we read questions. When we see standard deviation, it doesn't necessarily mean it's sigma. So sigma is only the symbol if it's population standard deviation. If we don't know sigma, the best we can do is rely on the information we get from our sample. So the sample standard deviation, it's been a while since we've seen this, but this is lowercase s. So what ends up happening is if we don't know something about our population, like the standard deviation, it introduces more uncertainty in our estimation process. So what we're going to see is greater margins of error when we're having to create a confidence interval based on S rather than on sigma. So we're no longer going to be able to use our Z distribution. We're going to need to introduce a new distribution that's similar to a Z. This solid line here is our Z distribution. So 0 at the center. So our new distribution also has 0 at the center, and it's called the student's T distribution. So a T distribution is always going to be wider than a Z distribution. So the wider is going to introduce these bigger margins of error. So the other thing with T distributions are there are infinitely many of them. So unlike our Z curve here, the standard normal, which there's just one of, T distributions will actually change shape based on their what we call degrees of freedom. So new concept here, degrees of freedom. The formula will be very simple though. It will just be our sample size minus 1. So essentially what will happen is when our sample sizes are small, degrees of freedom will be somewhat small as well. So over here on the graph, the widest graph dotted line there says degrees of freedom 5. Let's just compare that to the one above it. It says T distribution for degrees of freedom 20. So as the degrees of freedom gets bigger, our T distribution will begin to narrow. So small degrees of freedom, we've got a wide distribution, big margins of error compared to Z. As our degrees of freedom gets bigger, which means we're collecting more data, then our T distribution will begin to narrow, and eventually a T distribution basically looks just like a Z distribution once your sample size gets large enough. So we will definitely do a specific example coming up. So for now, the basic summary is we're not going to know population standard deviation. We'll have to rely on sample standard deviation, and this distribution will be used, T distribution, to find our confidence intervals in that case. And T distributions start to look similar to our Z curve, the larger these things, the degrees of freedom gets. And don't worry, we will of course do a specific example coming up.